Hi friends, our next chapter will be electromagnetic induction. In previous chapters, we have seen that when we have current carrying wire, that is, when we have electricity, that can give magnetic field lines. So, our question is the reverse effect possible? Electricity can give magnetism. So, can magnetism give electricity? This is the question. And answer is yes, it can. And that's what this chapter is about. By the end of this chapter, we'll get to know that the electric currents can be introduced or induced in closed coils when subjected to changing magnetic fields, and this phenomenon is called as electromagnetic induction. Let's move forward. The main hero of this chapter is Michael Faraday, because he's the one who conducted some experiments and basing on the results he gave us some laws about EMI, that is electromagnetic induction. His experiments can be mainly divided into three parts. The first part of experiment is that you have a coil here and you move a magnet uh, towards the coil in this way, and afterwards you move it away from the coil. So when you move the magnet towards the coil, you see that there is a deflection in the galvanometer in this way. That is, there is some current induced in this loop. And when you move it in the opposite direction in this way, you see the opposite deflection in this way. It means that when you move the magnet towards the coil, you had some current, right? And when you move it away, you have current in the opposite direction. When the magnet was stationary, no current was observed. Note that the current is observed only when the magnet is moving. Just see this one, you'll get a better idea. When the magnet is moved towards this coil, you see a positive deflection towards the right, and when it is moved away, you see a negative deflection. Observe that there is no deflection when the magnet is stationary. You see the deflection only when you have this motion. Okay, let's move forward. So, what if I reverse the magnet? I mean, if this is my position now, here I place the south pole and here north pole, of course, and the magnet is here. And what if I conduct the same experiment? I move it like this and like this. Similar results are observed, but just in the opposite way. Here I had north pole, right? So when I moved towards the coil, I had a positive deflection. So when I do the same thing with the south pole, when I move the south pole towards the coil, I get a opposite deflection now. That's it, and vice versa. Similar results are observed. And the second part of Faraday's experiment is this one. The same experiment is conducted, just instead of magnet, he used a current carrying loop. This is a potential source and you have current carrying loop here. In fact, we should get similar results because after all, a magnet gives magnetic field lines, right? And here the current carrying coil is doing the same thing. It's just giving magnetic field lines. So you are bound to get the same results. And similarly, if you turn the current carrying loop in reverse direction, I mean, it is something equivalent to rotating the magnet. That's it. And there is one more thing I need to tell you. If you move the magnet faster, then the deflection was observed to be more. More deflection was observed. So just note all these observations. We are going to draw some results basing on these observations. Basing on these two experiments, you may conclude that the current or EMF is induced in a closed coil when there is relative motion between the coil and something which gives magnetic field. This may be your guess, but the game is not yet over. You have this third part of experiment. Here you don't move any coils. There is no motion between these two coils. The thing is, you have a coil which has some key. Now, when the key was open, there is no deflection. Observe this. When you close the key, what happens? Current passes, right? So, when you close the key, there is observed a momentary deflection and it doesn't last forever. See, here even the key is closed in part C, still the deflection is 0 here. And when you open the key again, you find negative deflection. So, You have some deflection only when you close the key and open the key, only at that moments. So we are able to produce EMF in a closed loop even without any relative motion between these two coils. So what can we infer from these observations? It's not about the motion or relative motion. What is common in all these three cases is the magnetic field is changing closed loop, inside this closed loop. So it's not about motion or relative motion, it's about the change in the magnetic field. Actually, to be precise, it's not even about change in magnetic field, it's about change in magnetic flux. What is magnetic flux? In electrostatics, we had electric field and electric flux, right? Similarly, we have magnetic field and magnetic flux here. Magnetic flux is given by the dot product of magnetic field and area vector, that is BA cos theta, where theta is the angle between magnetic field and area vector. If this is the area, this will be the theta, okay? And if you have some area and non-uniform magnetic field over that area, then what to do? Divide that area into smaller parts and add all the fluxes due to each individual part. That will be B1 dA1 plus B2 dA2, similarly, and so on. You can write it as sigma bi dot dai, where I is from 1 to n, something, all. Okay. Now, basing on these observations, Michael Faraday gave us some laws. He said that change in magnetic flux induces EMF in a coil. So, in the first part of experiment and second part of experiment, you observe that the flux is changing because of the movement of magnet or coil. The magnetic field was varying and hence the flux was varying. In the third part of experiment, initially the magnetic flux in this loop was zero, and suddenly when you switch the current on, there is some magnetic flux through this. So there is a change in flux, right? That's what gave you the EMF. And what about that? When we moved the magnet faster, we observed greater deflection, right? So the rate of change of magnetic flux also matters here. Basing on all this, Faraday gave his law of electromagnetic induction. That is, the magnitude of induced EMF in a circuit is equal to the time rate, or simply the rate of change of magnetic flux through the circuit. The magnitude of EMF is given by rate of change of flux. This is clear. Of course, if you are so bothered about sign, take it minus here. This gives the direction of the electricity that is induced, but don't bother about it. In our next section, when we discuss about Lenz's law, I'll explain you in detail how to get the direction of that induced current. Now, if you have n turns, a closely wound coil of n turns, then the EMF will be n into the same thing. Okay. So you have to vary the flux. You know that flux is BA cos theta. So you can vary the flux either by varying B, or either by varying A, or either by varying theta. Okay. In the experiments we discussed now, the change in flux was due to the variation of B. You can also change the flux by, say, shrinking a coil or something like that, by changing the area. The third case, by varying theta. The example of that will be the problem that we are going to discuss now. Observe carefully. A circular coil of radius 10 centimeters, that is 0.1 meters, and 500 turns, and resistance, say capital R, 2 omega, is placed with its plane perpendicular to the horizontal component of Earth's magnetic field. Say we have horizontal component of Earth's magnetic field into the screen, and it is given as 3 into 10 power minus 5 Tesla. This coil is placed perpendicular to this one, okay, in this way, and this coil is rotated about its vertical diameter through 180 degrees in 0.25 seconds. So time is 0.25 seconds and it is rotated through 180 degrees. Okay, estimate the magnitude of EMF induced. Okay, say the area vector is pointing into the screen, so my initial flux will be initial, it will be BA cos theta, that is 3 into 10 power minus 5 into area is pi r square 10 power minus 2 and cos 0 is 1. This will be my initial flux, that is nothing but 3 pi into 10 power minus 7 WB. WB stands for Weber, it is a unit of magnetic flux, and my final flux will be, yes, it will be the same thing. Instead of cos 0 I'll get cos 180 here, so it will be minus 3 pi into 10 power minus 7 Weber. So my net change in flux is 6 pi into 10 power minus 7. I have the EMF given by n into delta phi by delta t. So I can write it as 500 into 6 pi into 10 power minus 7 by 0.25 seconds, which is nothing but 3.8 into 10 power minus 3 volts. Now I want to find the current also, which is given by EMF by resistance. That's nothing but this EMF, you know it, and resistance is given as 2 ohms. So it will be 1.9 into 10 power minus 3 amperes or 1.9 milliamperes. You just note that the values we found of EMF and current, or just the average values. I mean, you don't know how the loop is rotating, right? It may be possible that the loop rotated very fast in the first quarter of its cycle and then slowly and finally something like that. So we are not going into that details. We just assume that the loop rotates uniformly. Actually, the values of E and I, the instantaneous values of E and I are different and they depend upon the speed of rotation at at a particular instant that we want to calculate. Hope everything is clear till now. In the next video, I'll tell you what is Lenz's law and possible motional electromotive force also. Keep watching. Bye.